So on Friday, we left off and we're talking about muscular fatigue, and the last thing we got to do was watch that pretty funny video of the two ladies struggling to cross the finish line, where they were definitely showing signs of hitting the wall. Kind of leading from muscular fatigue is this concept, and I kind of pulled this information from my exercise phys book, are ergogenic aids, which are basically anything that is believed to increase performance. Okay. It could be as simple as stretching before a race, okay, because people think that stretching is going to help them run better or jump better or whatever. And there's evidence that states that probably is the case. But it could be as complicated as ingesting certain things. Okay. The other day we talked about creatine phosphates, which is that source of ATP for our muscles for high intensity maximal contractions, somewhere like 10 to 15 seconds. Okay. You can supplement and get this over the counter. This supplement is called creatine monohydrate, which does increase phosphocreatine levels in the muscle, and therefore helps people increase their ability to maintain force and power output. What type of athletic events would a person ingest creatine monohydrate? Bodybuilding, weightlifting, kind of the best examples. Okay. Any type of power workout. Okay. Not your I'm going to run a mile or 10 miles. Let me load up on my creatine phosphate, because as we know, that creatine phosphate is only going to give your energy for a few seconds of that maximal type exercise. Carbo loading is a beneficial form of ergogenic aid to increase your glycogen levels in your skeletal muscle and liver, which we know glycogen is your stored form of glucose, which we use to make ATP. What type of event would carbo loading be beneficial for? Marathons, okay, running long distances, swimming long distances, okay, hour plus type activity, not running a 5K in 25 minutes. Okay, you're not going to come anywhere close to depleting your glycogen in that short amount of time. Caffeine is actually, I always throw caffeine in here because it's college kids' best friend a lot of times. May improve performance at the muscle or nervous system or delivery of fuel to muscle. Can elevate blood glucose and increase fat utilization. Can decrease the perception of fatigue, lower the rate of perceived exertion during prolonged exercise. So it can actually do a little bit of short-term, but it also can be more long-term and benefits. So that's pretty cool. Something as simple as a 5-hour energy or a Red Bull or something like that can be helpful. So there's a lot more. I just want to kind of introduce some of the kind of most common ones to you guys. All right, kind of switching gears. I want to talk about the neuromuscular junction and motor neurons again. Last week we learned about the motor end plate, which is the side of the muscle fiber across the cleft from a neuron, specifically the synaptic end bulb. Okay, those structures form what we call the motor end or the neuromuscular junction. Okay, and each skeletal muscle fiber has only a single neuromuscular junction, but the axon from the motor neuron branches, and therefore we can see in our left image, in our green motor neuron, a neuromuscular junction for not only one but 3 singular muscle fibers, and 2 for the purple one. When that signal comes down those 2 different neurons, it's going to send the signal to all 3 of those muscle fibers, or all 2 of those muscle fibers at the same time. Therefore, all those events occur that we talked about the other day. Calcium is going to be released, troponin and all that stuff will occur, muscles will contract. All those fibers contract in unison. Okay? If you have a whole bunch of muscle fibers innervated by one singular motor neuron, it's going to provide us with more strength contraction, or bulk control. Whereas if there's very few, it's going to provide very fine motor control or muscular control. Okay? It can be as few as 20 in fine motor control, providing very precise movements. Okay? We're going to find this type of, or these types of motor units in the muscles in like our fingers and hands, allowing us to be very precise with our manipulation. Some of us have really nice fine motor control. I do not. You've seen my handwriting and my artistic ability, okay, versus other people that can draw. And I can't even draw a straight line with a ruler. Okay. Our finest actual motor control is by way of our 6 extrinsic eye muscles that move our eyes up and down and around and around in a very, very specific and very precise manner. Okay. Bulk or strength motor control is going to be found in our bigger muscles, like our butt muscles and our back muscles, our leg muscles, providing really good, strong, large-scale, powerful movements. Now, this first sentence on the next page is a direct, I think, anyway, copy and paste from the words that were on the sentence that was on the previous page. So I'll read through it again. A single nerve impulse in a somatic motor neuron elicits a single muscle action potential and all the skeletal muscle fibers with which it synapses with. Action potentials always have the same size in a given neuron or muscle fiber. Remember when we talked about action potentials? We said they always top out at positive 30 or 35. For neurons, it's the same in muscles. But the force that a muscle fiber produces can be different. Okay? We use the word force or tension interchangeably here. Okay? Muscle fibers will produce much greater force when there's a series of action potentials zapping it, basically. Okay? So it depends on the rate at which nerve impulses arrive at the neuromuscular junction. And for this reason, we call it, or measure it as, what we call the frequency of stimulation. Now, zapping it once is what we call a twitch contraction. It's a brief contraction of all the muscle fibers in the motor unit in response to that action potential. And this can be done in a lab setting with either directly stimulating the fiber or by the motor neuron. Okay, and there are 4 periods to a twitch contraction, and those 4 periods are shown here on the next page. The first phase is called the latent phase. The word latent is something that we've seen before, means delay. Okay. Down at the bottom is our graph to illustrate what happens during a singular twitch. We are showing down here at 0 milliseconds with this arrow the actual stimulation. So this is where we zapped the muscle fiber. And we're measuring tension, but right away, for a very short amount of time, nothing happens in the way of tension or force production. Okay. It's very short, only 2 milliseconds. And this is because those events that lead up to a muscle contraction are occurring. Action potential sweeps over the sarcolemma, calcium is then released from the SR. After that, we then contract. Okay. Contraction period is obviously where the contraction occurs and tension is forced. It can be as short as 10 milliseconds or as fast or as long as 100. Okay. And this involves all that stuff that we learned about the other day, calcium binding troponin, shift to tropomyosin. Binding sites are exposed, myosin forms a cross-bridge with actin, and it undergoes the power stroke. And peak tension develops in the muscle at this point. Okay. Then we relax, and we know that's where calcium's moved back in the SR, shift in the tropomyosin to cover those binding sites, cross-bridges are detached, all that wonderful stuff that we learned about the other day. There is not a refractory period labeled here, but it's going to be on the left side of our graph. And this is the same thing as what we talked about when we talked about neuron refractory periods. And I kind of compared this at the time to jumping in the air. Okay. Remember, you cannot generate an action potential in a neuron if it's still in the state of an action potential. Not until we reach back to resting membrane potential. Just like you can't jump a second time if you're still in the air the first time. Okay. You have to hit the ground and then jump again. Okay. Well, in muscles, the same concept occurs. Okay. If you don't allow it to go through the contraction process before, or you can't contract it again if you're still in the contraction process, basically. Okay. Now, if you zap it a second time before you completely relax, it's not going to just top out just like it did before. Just like we saw in neurons, if you zap a neuron, you're going to see summation occurring. Okay. And so we'll see the tension increase. And that's what I want to talk about right now. Remember, summation meant additive, or adding local or graded potentials together, which helped us get to that threshold. Okay? Well, the same concept exists in muscle fibers. Okay? If you hit it with a second stimulus before relaxation and after the refractory period, instead of topping out the same force that we saw the first time, we add it to it, and therefore force of contraction goes up. We call this wave summation in muscle fibers. Okay? Now, if you continue to do that, hitting it with action potentials, it's going to continue to add up. Okay? Now, if it does not top out, we're going to call this incomplete or unfused tetany. Okay? The strength of contraction continues up and up and up, but eventually we will reach fused or complete tetanus, which is where there is no relaxation period between the twitches, and therefore the contraction appears to be smooth and sustained. So it's not herky-jerky, it's just nice and smooth throughout. Okay. Now, you've seen the word tetanus before, I'm sure. Okay. In fact, we talked about tetanus toxin back when we talked about action potentials in neurons. Okay. You get a tetanus shot to try to prevent this from happening when you step on a rusty nail. Okay. You hear people describe getting lockjaw as a result of not getting their tetanus shot. Okay. Lockjaw occurs because your muscles in your jaw are stuck in tetany. Okay. And therefore they're stuck in contraction and they're completely contracted. Okay. And therefore you can't open your jaw because you can't relax those muscles. So if you step on a rusty nail, get yourself to the hospital and get that tetanus shot. Okay, kind of bouncing back to what we were just talking about a little bit ago, which are those motor units, the muscle fibers and the motor neuron that innervate them. We recruit them differently, and the process in which we do is called motor unit recruitment. Typically, different motor units of an entire muscle are not stimulated to contract in unison. So if I'm lifting this stick up, I'm not using all the motor units in my bicep muscle. Okay? So I don't need to, because it doesn't require all of the force that I can produce. Okay? So while some are contracting, others are relaxed, which actually helps to delay fatigue. Okay? They can kind of interchange between relaxed and contracted so that they're not always contracting, which would get us to fatigue quicker. Okay. We will recruit the weakest ones first, as you can see down here at the bottom, motor unit 1 recruited, which are going to be containing smaller fibers. And if we require more force, we'll recruit medium-sized fibers, motor unit 2. And if we require a lot of force, we would recruit motor unit 3, which is where you find the larger fibers. Okay. Recruitment is one factor responsible for producing smooth movements rather than a series of jerks. That way, when we lift something up, it's not going like this. It's going nice and smooth. And now, what I'm doing right now is performing one of the two major types of contractions, and we'll get to that here in just a little bit. First, I want to talk about muscle tone. Something that we've actually talked about before. We learned about this back when we talked about the brain. Even when we are at rest and we think our muscles are in a complete state of relaxation, they are still under contraction. At least very, very weakly, but still a little bit of contractions. And these are involuntarily controlled. Okay? So we cannot suppress them with our own conscious awareness. Okay? It's established by neurons in our brain, back in our structure that we learned about previously. That then sends signals down to our spinal cord. That then excites the motor neurons out of the spinal cord. That then releases small amounts of acetylcholine, a little bit of binding to the receptors, a little bit of depolarization, yada, yada, yada. Cross bridges are formed, and we're producing very small scale contractions. Okay. That's as long as there are motor neurons innervating and having connections to those muscle fibers. If you cut off the connection, you can cause your muscles to become flaccid, which is a state of limpness, which muscle tone is lost. Okay? And this means that the muscle's not going to be able to work, because there's no signal to it. And so when somebody has paralysis, their muscles are in a flaccid state. To sustain muscle tone, small groups of motor units are alternatively active and inactive. Okay, as I was just saying, as I lifted up my stick and dropped it back down, I was performing one of the two major types of muscle contractions. I don't want to talk a lot about this, but it has everything to do with whether or not the muscle is changing its length. Okay. The other name for isotonic is dynamic, which we've learned that word several times this semester. Dynamic means changing, whereas static, remember, meant staying the same. Okay. We call it dynamic because the muscle changes its length. And that's what I was doing with my meter stick because I was lifting it up and lowering it back down. I was contracting and shortening my biceps, so I was bringing it up in a concentric form of isotonic or dynamic contraction, and then I was lowering it back down, and therefore the muscle was extending or lengthening, which is called the eccentric phase of the muscle contraction. Okay. If you're a weightlifter, these are terms you may have learned about before. Okay. One of the rookie mistakes that I see people that are new to gyms do is pretty much ignore the eccentric phase of a muscle contraction. They lift the weight up and then they drop it back down. Okay, that's very hard on you for a lot of reasons, but it also takes away one of the really beneficial aspects of the weightlifting process. That eccentric phase is where a lot of the strength gains can come from. And Urban, this is probably hitting home right for you since you want to open a gym someday. So make sure you always want to promote those eccentric phases. Now, isometric contractions are where the muscle is not changing length. As you can see, I italicized does not change, versus up here I italicized changes. Okay, the book example here is okay. My favorite example is doing a wall sit. Okay, if you've never done a wall sit before, they suck. Okay, I had to do them a lot when I was rehabbing my knee in college. What they have you do, if you're not familiar with it, is get into a squat position and hold your back up against the wall and pretend like you're sitting on a chair. Except you're not sitting on a chair. You're holding yourself up by the leg muscles that will eventually start feeling like they're going to explode. Yeah, you do it for a minute, 2 minutes, your muscles are going to start shaking. You're going to feel really weak. You can tell definitely you're contracting your muscles, but there's no change in length occurring. Okay. They're great when you're rehabbing things like your knee because you're not putting the knee through a range of motion, okay, and therefore still helping to get strength back without really, putting the knee, in that case, at risk for damage. Okay. Some sports use isometric contractions. Most use isotonic. Think like isometric, you're thinking like ballet or gymnastics. Okay. I always think of like the rings. They have to hold themselves out from the rings with their two outstretched arms. Okay. You ever try to do that? I can't do it. I can guarantee you that. Gymnastics athletes are actually some of the very strongest pound for pound athletes in the world. All right, for the next couple slides, I want to talk about the fact that our muscle fibers will vary in composition and function. You can open them up or look at them. Performing a muscle biopsy will show that muscle fibers vary in their content of myoglobin. We learned about myoglobin last week. It's that oxygen-storing protein in our muscles, similar to hemoglobin that we're going to talk about in our next lecture. I talked about how people think that the red coloring in steak is blood, when in actuality it's this myoglobin. If muscle fibers have a bunch of myoglobin, which is going to cause that red color to appear, we can classify those as red muscle fibers. Okay? This is where dark meat comes from. You ever wondered why there's dark and white meat in chicken and turkey? Okay, the dark meat, which in my opinion tastes much better than the white meat, is going to be this red muscle fiber with lots of myoglobin. Maybe the myoglobin makes it taste better to me. I don't know. Okay. Now, red muscle fibers have more mitochondria and are supplied by more blood capillaries than your white muscle fibers. Okay. Those kind of three things go hand in hand because they involve the production of ATP aerobically with oxygen. Okay. Myoglobin stores it. Mitochondria is where the ATP production of, or the aerobic production of ATP takes place. And then blood capillaries provide an avenue for oxygen to get into the muscle. White muscle fibers are going to be much lower in content of myoglobin and are going to appear whiter or lighter, which is why chicken breasts are going to be the white meat. Skeletal muscle fibers also contract and relax at different speeds, varying which metabolic reactions they use to generate ATP, how quickly they fatigue. Based on all these various structural and functional characteristics, we can classify those our muscle fibers into three major types: type 1, type 2A, and type 2X. We'll spend the next 3 slides discussing differences between them. So you've got kind of 2 ends of the spectrum. Okay, on one end of the spectrum is where you find type 1. And I think you have to write out the type 1 in there. It's not type I, that's a Roman numeral. Okay, so it's type 1, it's an uppercase I. Then you've got 2A. These are kind of down the middle. And then on the very end of the opposite spectrum from type 1 are the type 2X's. So let's talk about type 2X, and I'll go back to type 1, and then I'll talk type 2A, since I'm on this page 2X. Okay, so on this side is type 2X. 2X are large and therefore really powerful. Okay. They have a low myoglobin content, so there's going to not be very much myoglobin in them, and therefore that's why they appear white. They have relatively few blood capillaries, few mitochondria, because they make their ATP outside of the mitochondria, and they make their ATP by glycolysis, an anaerobic process. Okay. And glycolysis takes place in the cytoplasm of cells. These contract strongly, quickly, fatigue quickly, though. Okay. They're adapted for intense anaerobic movements of short duration, like powerful things, weightlifting, throwing a ball, jumping, sprinting. Okay. As you can see over here on the table, track sprinters, their fibers are going to be 70 to 75% type 2X. Okay. Let's go back to type 1s. They're on the opposite end of the spectrum. They're very small in diameter, therefore have the least amount of power that they can produce. They have a high myoglobin content, lots of mitochondria, appear white or appear dark red in color. A lot of mitochondria in order to produce ATP aerobically. They're slow in how they contract, but they are fatigue resistant. Therefore, can sustain muscle contractions for several hours. These are the type of fibers you'll find in your postural muscles, like the ones that run up your spine. And you'll find a lot of these in endurance athletes. So, like long marathon runners. Okay, you probably have a lot of muscles like this, or fibers like this in your leg muscles. Okay. Right kind of down the middle between type 1 and type 2X are the type 2As. Okay. These are intermediate in size. They do have a lot of myoglobin. They do have a lot of mitochondria. But they also make ATP by glycolysis. They're also fatigable, but they're not as fatigable as type 2X. They are kind of medium in speed of contraction, and they're going to be good for walking and sprinting, okay, which is kind of a medium pace, especially the walking aspect of things. Type 2-1 or type 2X and type 1. Okay. Now, type 1, type 2A, type 2X are kind of the old school terms to describe them. You notice that I've also included, and these are what your book goes with, slow oxidative, fast oxidative glycolytic, and then fast glycolytic. Go ahead and know those other terms, but there's a good chance I'm going to go with the type 1, 2x, 2a's. Anybody know our primary determinant on composition in our muscles? What we're going to have, why we're going to have it? Genetics. Okay. My dad was a pretty successful sprinter in high school. I was a pretty successful sprinter in high school. So were my siblings. Okay. Probably a good chance Caitlin's parents were pretty good long distance runners. Maybe they did or maybe they didn't. Okay. Now does that mean training can't alter it? No. But genetics is really, really a big factor. The most important factor. Now, we've talked this semester about certain diseases and interferences with homeostasis. Okay. When we talked about the nervous system, we talked about actually botulism toxin. Okay. These are ways to interfere with normal muscle function, therefore impacting homeostasis. We learned previously about that neuromuscular junction, which is where motor neurons meet muscle fibers and all those events that occur there. Well, since there are so many different factors and things going on, there are different ways to interfere, and drugs and paralytic toxic agents can do so. Okay. We learned previously about Botox, and the drug that is the synthetic form of botulism toxin, or botulinum toxin, as you'll see it sometimes. We get from improperly canned foods, blocks the release of acetylcholine from synaptic vesicles, and therefore the muscle fiber will never become excited. And therefore the muscles become temporarily paralyzed. And now if you get this in your respiratory muscles, it can be an absolutely life and death situation. As a small amount can paralyze your respiratory muscles, therefore you can't breathe. Not a good thing, obviously. Curares, plant poison used by South American Indians on arrows and blowgun darts, causes paralysis of muscles by blocking the receptors for acetylcholine. So it doesn't block the release of acetylcholine like botulism does. It just blocks the acetylcholine binding. Derivatives of curare are actually used during surgery as ways to relax the skeletal muscles. Organopesticides, instead of causing the muscles to relax, they cause the muscles to contract uncontrollably. They block that acetylcholine esterase, and that prevents acetylcholine from being removed from the muscle fiber. Therefore, the muscle fiber is going to continuously be excited. Okay. Myasthenia gravis, autoimmune disease, which the body produces antibodies to bind to acetylcholine receptors in the muscle cell. So it works just like curare. Okay. And then nerve agents work just like organopesticides. They inactivate the action of the enzyme, causing uncontrolled action of acetylcholine, therefore causing the muscles to contract. If you've never seen the movie The Rock, okay, it's an older movie, Nicolas Cage or Sean Connery in it. They talk about some of these things. These nerve agents, it's all about nerve agents in that movie. It's pretty cool. Very typical guy movie, so like explosions and high-speed chases might be up your alley. I tell you what, don't worry about this slide. I kind of decided just recently I'm not going to really get into it. It's really kind of more physics-based stuff, talking about how muscles and joints work together to form levers. Most of the time when I talk about it, it kind of just goes over the head of students. And you got enough on your plate, so I'm just going to kind of whiz past that. Last thing I do want to talk about is what training, and I talk training, I'm talking exercise training, can do to your muscles. Some of you guys partake in this. We were just having a conversation about exercise before class. Some of us don't, unfortunately, here in America. Regardless of the type of training, our muscles are going to adapt in a similar way. And it's pretty cool. So as it states there, regardless of the training program, whether it's endurance or resistance exercise, the exercise-induced adaptations occurring in muscle fibers is a result of an increase in the specific amount of proteins. Remember, since the beginning of the semester, we've talked something's happening in the body. It's probably a protein, and we learned the other day how many different proteins are found in your muscles. Training helps increase and provide protein adaptations. Stress of exercise stimulates cell signaling pathways and contracting muscle fibers that switch on transcriptional activators. This turns on specific genes to synthesize new proteins. We learned previously that transcription was the process where we make RNA from DNA. And then we take that RNA and we translate it into proteins. Okay, so our first graph over here shows for several hours after exercising, levels of RNA are going to be elevated. Therefore, we're going to be making proteins after exercise. Okay. These specific proteins that are transcribed, it should really say translated, but determine the muscle's characteristics and its ability to perform specific types of exercise. Now, a single bout of exercise is not efficient or is insufficient enough to produce large changes in proteins within the muscle fibers. But one exercise session does promote disturbances in cellular homeostasis that, when repeated over time, we can see definite changes occurring in the muscle. So, take-home message, exercise repeated on a daily basis does have a cumulative effect, leading to a progressive increase in specific muscle proteins that therefore improve muscular function. Questions on anything there?